Thank you. I will speak not exactly about Cozystack, but about the technologies we used and how we organized storage subsystem and how we utilize it. This is very interesting. I will start with introducing myself. Okay, now we have one slide back. So can we somehow synchronize it? Or okay, I'll just take a look at this screen instead. So I started my Kubernetes experience working for Vedos. Vedos is biggest Czech hosting company. We were doing a lot of interesting stuff, and I was working with Kubernetes, especially for bare metal. We were running Apache services and multiple virtual machines and things like so. Like it was very amazing, interesting job. Then I switched working for Pelerk. I was developing Deckhouse Kubernetes platform, where we introduced also virtualization and storage system, and now I'm founded a new company which is called Ionix, and we develop open source software for providing managed services, just like AWS, but on your own on-prem environment. The idea of the Cozystack that you can take bunch of servers and convert them into cloud system with Kubernetes API, with monitoring enabled, and all the opportunities inside. This is how it looks like. So you have dashboard where you can click and install any application you want to. You can run Kubernetes. You can run Kubernetes inside of the Kubernetes. The same Kubernetes, Postgres cluster, MariaDB, and things like so. Every application can be configured, so you can specify it like normal YAML in Kubernetes. It has its own Kubernetes objects. And now I'll share information how we actually built the platform. It consists of few layers. The layer 1 is operating system and Kubernetes, and we depend on Talos Linux here. On layer 2 we have storage. For storage we use LINSTOR. LINSTOR is open source solution which allows you to order PVCs on bare metal servers and enable replication for them. For networking, we use OVN. OVN is a solution which is specific CNI, which has extended opportunity to specify multiple networks and consume it for virtual machines. So it works well with KubeVirt. And for virtualization, we use KubeVirt. On top of this, we also built the layer of operators, cluster API, monitoring system. And on the final layer, we say application layer, where users can order their own services. We have managed databases, virtual machines, and managed Kubernetes. So today I'm going to show you how we utilize the storage and how we organize the system, how we deliver all of these components. From my perspective, it's a very interesting topic. So for layer 1, we use Talos Linux. Then the rest layers are managed by FluxCD. And finally, we have specific Kubernetes aggregation API server, which translates FluxCD resources to the Kubernetes objects. Let's first speak about layer 1, about Talos Linux. Talos Linux is Kubernetes-oriented distribution. It is very specific, and it can be used only for Kubernetes. It actually have the single purpose operating system to run Kubernetes clusters. It is not normal operating system which you can use like login over SSH, install some packets. It has single core, and it has API server which is very similar to Kubernetes has. So you can configure Talos Linux with a single YAML format, a single YAML config, and this is how it looks like. It has actually two sections, machine one, where you can specify configuration for the machine, and cluster section, where you can specify the configuration for your Kubernetes cluster. So in machine section, you can specify a type of machine, either control plane or worker, specify certificates, because Talos runs its own API. And it should listen on specific certificates. You can specify settings for networking. you can see also VIP address there, so it has built-in opportunities for load balancers, and disk to install the system itself. While cluster section includes endpoint, this is normal Kubernetes endpoint, which will be working after Kubernetes will up and running. The same certificates and configuration for Kubernetes components. So if you want to install Talos Linux, you just need to specify to write this configuration file and use talosctl apply tool to apply it to Kubernetes similar API server running on the virtual machine. After that, it will just start running, and you will have Kubernetes cluster ready to use. But with bare metal, you always have some issues because virtual machines are kind of similar, but bare metal servers are not. Since we are renting on ISPs and we interested to work with bare metal machines, we did some enhancements and some approaches we used to adopt Talos Linux for bare metal machines. So when you have bare metal servers, you always have to worry about firmwares and kernel modules, how to update them. You still have to worry about how to boot Talos Linux image on those nodes, because they usually have no virtual CD-ROM where you can install, where you can put virtual ISO. So you can do that through the PXE, or you can use APMI. Still questions about how to specify proper disks and interfaces for every machine, because we remember that every server is different. Every server has different MAC addresses and disks, and you need to find a convenient way to specify everything in this configuration. First, think about firmwares and kernel modules. We solve them by baking our own Talos Linux image. So we specify that it has specific firmwares and also kernel modules we use. For example, our storage is working right in kernel, and we use such modules like DRBD and ZFS. So you can bake your own Talos Linux image by writing similar YAML file where you just specify extensions you want to. Here are firmwares, and here kernel modules. So after this, you push this YAML file into Docker, and finally you get image which you can boot any method you like to. So you can use PXE or you can use IPMI. This image will hold all the needed kernel modules and everything you want to. For orchestrating this, we created our tool that's actually shell script, which allows you to start using Talos Linux faster. It's called Talos Bootstrap. We really like PXE method, so we also provide our image, Docker image with our image for booting. So, and this tool, you can use it to configure the servers. First, you boot servers from these Docker containers, then you use this tool for configuring Talos itself. This is how it looks like. It's actually, it can find all the nodes you have in your network. Then you can put host name, disk to install, some network settings, and finally it will generate Talos configuration, which will be then applied to the node. And node get installed. Actually, you can set up your own Kubernetes cluster on bare metal very quickly, and you'll get ready Kubernetes cluster to use. But that's not the thing. Inside of this, every virtual machine, you will have prepared image with exact kernel modules and exact kernel version. That actually allows us to do stable base for the rest of the system. And speaking about the next layers, how actually we deliver all of these components. We use FluxCD, but we do really interesting logic to start. Before you start using FluxCD, you need to somehow install FluxCD itself. And so you need to configure CNI and other stuff. before it can start working. So we let our users to apply a single configuration file, which will create one container, deployment with one container. Inside of this container, we have a repository with Helm charts, and we also have small shell script which will install CNI and Fluxcd. Then all the rest logic is get done by Fluxcd. So it delivers all the system components into the same cluster where it is running, using the Helm charts repository running in the same cluster. If you want to update the platform itself, we just replace this container with new one, and Fluxcd just delivers the rest of the components into the same cluster. This way, we achieved we made our environments reproducible, and they always have the same kernel, same modules, and the same components installed inside. This way we deliver the storage. The LINSTOR is the storage based on, it's not like storage system, it's more likely orchestrator. It's like Kubernetes, but for block devices. Kubernetes works with well-known technologies like LVM and ZFS, so it can cut volumes it can be integrated with Kubernetes itself, and it can cut volumes from LVM and give it to your workloads. If you need to have replication, you can use DRBD to enable replication of those volumes between the nodes. It also has some extra features. For example, it supports encryption, deduplication, but we don't use them right now. Actually, using LINSTOR on bare metal cluster allows us to have almost native performance of the storage system on the bare metal node. We also have networking, which is based on Cilium and KubeVirt. KubeVirt works well for virtual machines. It can remember MAC address and IP address, and it also allows you to live migrate virtual machines from one node to another. We ship monitoring system, virtualization based on KubeVirt, and all of these open source components from which our platform is made of. Here are some charts why we choose exactly LINSTOR over Ceph. We also use Victoria metrics instead of Prometheus because we really want to get most performance what we can get from the bare metal nodes. In those charts, you can see that it's usually faster almost in 7 or 10 times and more productive than the other upstream technologies. And finally, the most interesting part, how do we use this stack and how we use storage? We use it different for all of these components, for databases, for virtual machines, and for managed Kubernetes cluster we're running on top of this platform. By the way, all of these components, like managed Kubernetes databases and virtual machines, they are managed by operators. Only operators can provide you opportunity to have full lifecycle management for your application. So if you just use Helm charts, it can put some YAMLs into cluster, but it will not take care about the state. We have a hybrid approach where every application here is actually a Helm chart, but it puts YAML files for operators. And for all of these Helm charts, we also built our own aggregation API server, which translates them, actually Flux-ready resources, to Kubernetes objects. That actually allows you to simply extend the platform itself, the new type of resources, just by simplifying them as Helm charts. And let's speak about the storage itself. The database is managed by ordinary operators. We use CNPG for Postgres and StreamZ for Kafka. But we extended with our Helm charts we added extra logic for keeping dashboards, for Grafana, and configuring users. So actually, the storage we use for database Yeah, that's a set of operators we use in Cozystack. If you want to get any database installed, you just click and install, or you just specify YAML manifest in Kubernetes. Then it gets managed by operator framework, by operators, specific operator for this database. For example, here, if you want to create a Redis application, you can specify bare minimum of the parameters. It will create few resources like Redis failover for the operator, service for accessing, and also additional resource for the Victoria metrics. In terms of storage, we have this logic. Let's take a look. For example, we have 3 nodes. We have some storage pre-configured on them, and we don't use replication for database. We don't use storage-based replication. So we expect that database can be created in cluster mode, and it will replicate it on application layer. So in case if we create new Postgres cluster, it will create 2 Postgres replicas, and every replica will have its own volume on the node where is it running, and it will replicate each other and manage it by the operator. So this approach we use for databases, and those databases running right on bare metal nodes, which gives you ultimate bare metal performance. But in case if we want to let user running their own workloads, we can just let them running what they want to in our management Kubernetes cluster. So for user workloads, we always expect that user will create their own virtual machine or managed Kubernetes cluster. For virtual machine, the logic is the same. So we open dashboard, create virtual machine resource, which is actually Helm. It creates YAML for KubeVirt, and it's managed by KubeVirt, actually creating the virtual machine. From the storage perspective, we can't create multiple replicas of the same virtual machine because it does not work like that. The virtual machine can be running just once in single replica, but we need to have some redundancy for it. So when you create virtual machine, we use different storage class, which just creates 3 replicas for storage, and it also enables fencing. That means if node go down, the virtual machine can be moved to another node, and it will always work with the same storage, with the same PVC, which is now replicated. And the most interesting part, how do we organize tenant Kubernetes clusters? Yeah, we run Kubernetes inside of the Kubernetes. This is actually done the same thanks to Helm. We use Helm, which sets up components which are managed by Cluster API, Kamaji, and KubeVirt. Kamaji is, I would say, it's kind of operator for Kubernetes control plane. So using Kamaji, you can create custom resource which will create standard Kubernetes control plane components inside of the working Kubernetes. We use Cluster API to control this. Inside of the management Kubernetes cluster, we have this Cluster API that allows us to run multiple tenant Kubernetes cluster in specific namespaces. But there are still questions how to configure Cloud Controller Manager, CNI, and storage and cluster autoscaler, because it's not just simple run virtual machines and install Kubernetes on them. You need to have full integration with cloud to make this Kubernetes fully functional. So we use FluxCD to install all of these components the same like in management Kubernetes cluster and the tenant Kubernetes cluster, which just created and running with virtual machines. Inside of the management Kubernetes cluster, we have this tenant control plane, which holds all of these Kubernetes components like API server, controller manager, scheduler. We're also running separate CCM for KubeVirt and CSI controller. That's just part of the CSI driver, which controls creation of the volumes and attachment and things like so. We also have cluster autoscaler, which creates needed amount of workers. It takes a look inside of the tenant Kubernetes cluster, checks if it needs to create new workers, and actually create workers. Inside of the workers, we have CNI plugin installed, ordinary Cilium, and CSI node part, which is which controls the attachment of the volumes after it gets attached to the node. It can actually mount it and run for the volumes inside of the tenant Kubernetes cluster. Yeah. And now we are going to talk about this part, how it works. So if you run virtual machine, in terms of management Kubernetes cluster, this is ordinary pod. In case if you have 2 virtual machines, you have just 2 pods. If user runs inside of this virtual machine, inside of the virtual Kubernetes, their own pod, and this pod requires you to use some persistent volume claim, the new persistent volume claim and persistent volume in management Kubernetes cluster will be created. Then KubeVirt creates additional pod which calls hot plug volume, and it handles its own logic which will pass through this volume 1 into this virtual machine and then attach it to the pod. Slightly difficult logic, but it works. For user data, we can't be sure if they're running such things like Postgres clusters, so we always want to have this data replicated. So for this data, we also use replicated storage class, which enables this replication thanks to DRBD. In case if user runs pod on another node, it can also attach it on another node with the same logic done by KubeVirt project. This way we actually implement the fully functional Kubernetes, which has load balancers, persistent volumes, and a cluster autoscaling. Also the rest things which get used to have in every cloud. Cozystack now CNCF sandbox project. Thanks to our community, many features are appearing. Please join our community, and we have community meetings as well. I will provide some links about the projects I talk about. So the first is Cozystack, second is Talos Linux, which we use for operating system. Piraeus data store is the storage I was talking about, and set of my articles which describes how all of this working together. Here you can see other my speeches. If you're interested, I have many of them. Thank you. Now I'm ready to answer your questions.
So, when you install Talos on bare metal, how do you ensure that the disk is /dev/SDA?
Good question. The method I show in this presentation, I will not click it back because there are so many slides, sorry. So we have 2 methods. The method 1 is Talos Bootstrap. It was the tool which also manufactured by the reason that every bare metal server is different and we need to get this information. Talos Bootstrap allows you to provide a list. How this list generated, it's just API call to Talos API before the config is applied. We also have another tool which allows you to declaratively set up Talos itself. It's called Talm, just like Helm, but Talm. It's like Helm for Talos Linux. It allows you to use tools like lookup, functions like lookup, to query Talos API and generate your config with your own custom logic.
Okay, second question. How do you handle the node eviction, failures, upgrades?
As about upgrading, thanks to Talos, some logic is automated. So in case if you want to update your node, you can apply a new configuration file, then run one call, which will first evict all the pods from the Talos, from this exactly node, then reboot the node, then turn it back to the cluster and remove this taint. As about failures, this is a good question. For now, we have storage-based fencing. It is also supported by Piraeus project, by LINSTOR. So with the storage, it ships specific controller, which checks if, I would say every volume in Kubernetes in LINSTOR, it has quorum, and if quorum loss, then it can guarantee you that the workload can be running on different nodes. So in this way, it will just go to Kubernetes API, remove the pod, which currently can't be running on another node. And this way, the high availability will be ensured.
Okay. Is there any question from audience? Here. Wait.
So my question is about the layer 4. You said you can define it with YAML, like database or something. So can you have it like in some Git repository and then Cozystack will scan it? Or?
For now, we're trying to build everything in tree. So we distribute the platform the same way. We have repository inside of the platform. This is not Git repository, it's Helm charts museum. But all of this is built out of the Git source tree. You can take a look at our source code. All of those Helm charts and configuration is stored there. So if you want to extend the platform with new types, you can actually specify new Helm charts in this. For now, you actually need to rebuild the platform. But all you have there is just simple YAML configuration. So the platform itself is fully built. I would say it's written on YAML, on Helm templates. And to extend those kinds, we just have a config map which describes which kinds should be translated to different Helm releases. This is done by Kubernetes segregation API server.
So in the Helm chart, it's like some resources that will be then picked up by some operator?
Yeah, inside of Helm chart, you have a few resources for the operator.
Yeah.
This way we have flexibility because you can specify your own custom Helm charts and you can specify specific values which are possible to change by the user, because you don't want user to change everything in operator. They can overwrite image and compromise the management cluster. So if you need to add your own application, you create your own Helm chart. In values, you specify the values they allow to change, and then extend configuration file for our API server, which also publishes it as Kubernetes object. It's pretty similar to CRDs, but without state. So we don't sync the state between our custom resources. They translate it on the fly.
Okay. Thanks.
So we have another question in Slido. So what would happen to Cozystack if Cider Labs bankrupted and Talos would stop being developed?
Good question. We are not very dependent on Talos Linux. Moreover, we're about to add another support of Ubuntu and other public distributions. So the main value of Cozystack is to provide ready configuration, ready to use of all of these open source components. And Talos Linux is just one of the components which is replaceable.
Any other question? Oh, okay.
Thank you for the talk. So the Talos doesn't have any package management, but you can install some modules there. But if there is, for example, NVIDIA modules, it needs DKMS. So can you install some binaries to the Talos or not?
Thank you for the question. Talos itself can be configured on the build phase. When it already built, there is no opportunity to inject any modules, so you can't even use some kind of DKMS, or the insmod command is prohibited by the kernel itself. You can inject only modules which have compiled while the Talos Linux, while the Linux kernel was built for the Talos. So the Talos itself have the structure of such packages, but they can be used only while you're building your own custom Talos Linux image. If you use factory.talos.dev, they also use this extension, so you can specify with the check marks the modules you want to, and in output you always will have one single image baked, which you will just use with no opportunity to inject any custom modules inside of them.
Thank you.
So, no other? Okay, so I have one. How do you handle disk encryption?
Encryption? Disk encryption?
Disk encryption.
We actually rely on LINSTOR logic. It has a LUKS layer, so you can create additional config map or secret with master passphrase. And then in your storage class, you can specify that these volumes should be encrypted. And then it will create, like usual, ZFS. We use ZFS, but it can also work with LVM. So it creates some block volume. On top of this, it creates LUKS. And on top of this, it creates DRBD, which also replicates it between 2 servers or even more servers.
Okay, thank you. If there is no other questions, so thank you for your talk.
Thank you for listening.
And we can continue the networking part, so don't leave it. Just take some food and we can talk about what you want. So, thank you.